The next lecture in this section talks about this E. E is not a letter in mathematics. It's a symbol like pi. E, if you recall, is equal to 2.71828. And we can find that, and by the way, that continues and never repeats, so it's an irrational number. If I find E on my calculator, if you recall from logarithms, which is what we're going to start studying here, it was under an ln. So I take e to the first, and there's my value of E. E was known as Andrew Jackson's number. Remember, he was two-term 7th president, elected in 1828. Okay, where does this E come from? Well, E is pretty important because it occurs naturally. And what happens if we take this expression and take it to the n and look at it as n gets large? You might think that, well, 1 over n, or 1 over a large number, is 0, about. 1 plus 0 is 1. 1 raised to a large number should be 1. But that's not the case, because 1 over n really isn't 0. So let's go ahead and type this in. So I've got a parentheses, a 1 plus, and then I need to go ahead and put parentheses. And let's say our large number is 1,000. Not real large, but large enough. So I close my fraction, I close my expression, I raise it to that same n, or 1,000 power. When I look at that, am I approaching E? I am. And what happens with this is, you'll see in an application section, that that's really how money grows. It happens to do with keeping 100% and adding it a rate compounded so many times. And so we call this the natural logarithm. So we're going to call this a natural exponential. So we can have any base on an exponent, but when we use a natural, we're going to use e to the power of x. Now, when we study exponents and logarithms, they actually go together. We're going to use common bases. So we're going to use base 10. We are in the base 10 system. For example, base 10 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. And if you look, there are 10 numbers there. As soon as I get to my next one, I've got to start switching positions. And so it takes 10 symbols. Another base that we're going to be using is base E. And you're thinking, well, 2.7818 plus symbols. Well, it's going to be really handy because it occurs naturally, and there's a lot of things we can do with that. So if we take a look at the graph, each one of these has a start value of 1. If you recall, y equals a times b to the x. In this case, b is 2. That's my factor. In this case, b is 3, my factor. Notice it got bigger. And in this case, e is my factor, and it's approximately 2.71828. So if I was to graph these, they would all hit this point. So I'll graph the first one in blue. I'll graph the next one in red. It's going to be steeper, and so it's going to come down here, hit here, and go steeper. And then the green one, well, this fits between those two. And so it's between those two, hitting that point, that common start value, and coming through here. So E is a very, very important number that we want to know about because we're going to use it when we do our applications, and it has to do with compound interest and so forth. So we have two ways to compound. One would be annually, which would be one time a year. And we have this thing called continuously. That would be every millisecond, just over and over and over again. Obviously, you'd want your money to be compounded in this way. So there's a formula that we're going to use for compound interest. And here it is. What I accrue over time, accrue or get, is the principal, the amount I start with, 1, all the money I invested, plus the rate it's invested at over the number of times I calculate interest, raised to the number of times I calculate interest, times the amount of time I'm going to do that for. So if we look at this and transfer it here, it says invest $5,000. That's P. That's my initial investment. My rate is 3%. My time is 10, and N is 1. Compounded one time every year. So when I put in my formula here, I get 5,000, keeping my 5,000. My rate over 1. So I just split that rate up into how many times I compound it per year. and 1 times 10 years. So on my calculator, you need to make sure that you understand that this needs to be in parentheses and any fraction needs to be in parentheses. But as I look here, I can see that 1 plus 0.03 is 0.03. So on my calculator, and you don't need a graphing calculator for this, so you're going to type in 5,000, parentheses 1.03. This is my decimal there. And I'm going to raise it to the 10th power. And it looks like the amount I'll get out of that is 6,719.58. So it's just using that formula. So let's try another one, because it's a different formula, so you're going to want to know these. Okay, so the next formula that we're going to use would be the amount of money I accrue over time is equal to PERT, P-E raised to the RT. It's a lot easier, but never is your money compounded continuously. You want it to be. Only your debt is compounded continuously. So if I plug in the values for PERT, the amount of money I get at the end is equal to the amount of money I start with, e to the rate, which is 0.03, times the amount of time, which is 10. So again, you got to plug this in your calculator. You have to know where e is. So I plug in 5,000, parentheses, e, which I go and get e, which is second ln, and it's to the 0.03 times 10. And then I'm going to close my parentheses, and notice it gets me more money, 6,749.29. Not a lot more, but enough. Think if you had $100,000 in there. So you can see that you will need a graphing calculator. Now there are problems on web work, and that's how you'll turn your homework in. The problems that the class will be working on page 336. So you can also look at those for some extra practice.